Now we try to derive the same. We just saw that we derived the equations of motion by using Gauss's integral theorem, which relates the surface theorem with the which relates the volume integral with the surface integral. Now we try to derive this by using calculus or by using infinitesimal control volume. So for this one, we choose a small infinitesimal volume that is shown here in a large image size, just for convenience of understanding things. And a rectangular coordinate system, as usual, is chosen in the x, y, z direction. And in the x direction, the velocity component is u, is assumed to be u, and let v be the velocity component in the y direction, and in the z direction, the velocity component be w. And for this, we try to use the Taylor series expansion, as we have mentioned before also. And you will recall that the Taylor series can be expanded for any function f of x about a particular point. So similarly, this also at a point P, about the point P, we try to expand the Taylor series and try to find out the components that occur. You will see from this box that there will be 6 phases altogether where the fluid motion is taking place. The fluid is coming in, the fluid is going out, and we have to see the change in the fluid in that small change in time, delta t. The red dots are the center of the 6 faces of this cube. If I try to expand the value of rho u for the center right face, because from one side there is a fluid that is moving in and there is another side where the fluid is moving out. So there are 2 faces, and therefore for rho u, that is on the right hand side, we obtain the equation to be, we have to recall that f of x will be equal to f of x naught plus f dash x 1 by 2, the first derivative, and similarly this will be 1 over 2 factorial plus f double dash, etc. And this continues into dx and so on. So similar terms are here. You are all familiar with this, so I don't want to go over that. If I write the same equation in the same way for the value of rho u, because we are trying to calculate the total mass of fluid that is moving out, so it will be rho u plus the first term and then second term, and then there will be infinitely many higher order differential terms. We try to take a linear approximation, and therefore we ignore the higher order terms and we try to take only the linear component, and therefore the first term we will retain and ignore the higher order terms. By doing so, we obtain 3 terms: center of the face, center of the left face, and center of the front face. And remember that there are other terms also that we have ignored. So we are not bothering about them, and we are only trying to take a linear approximation. And this sign is, that is why now not equal to, it is trying to show that it is approximately equal to this, because we have abandoned certain terms. We have struck off a large number of terms which follow this one. So the cube that has 6 faces, 3 terms are of this type, and then there will be another 3 terms that are from the rear face, the top face, and the bottom face. And this sign is a negative sign. We have written here mistakenly. And remember, this is rho because there is density here. So rho stands for density, while u, v, other components, you know that they are with respect to the velocity components. So we have these three components on three faces, and the remaining three components from the three faces. So altogether there are 6 faces of the cube, and we will add all these terms together. Then we try to find out, to reduce them to the continuity equation, and arrived at a consolidated result. Remember, I have made some corrections about the typing errors.